time for another quiz. All right, quiz 10. Here we go. This one's a good one. I'm looking forward to what we're going to see this week. All right, number 1. Find the limit as t goes to 0, cosine of 3t minus 1 minus t squared. Divide that by e to the t plus e to the minus t minus 2. Now the first thing you always do with any limit is you ask, well, let's just plug in 0 or whatever we're approaching and see what we get. So what do we get? Well, we're going to upstairs, cosine of 0, 1 minus 0 squared divided by e to the 0, 1 plus e to the minus 0, still 1, minus 2, or 0 over 0, which of course 0 over 0 equals more work. It's that indeterminate. We don't know what it is. So we got to do more work. Well, what do we do? What's the more work? Well, when you see 0 over 0, the answer is l'hôpital. Oh, l'hôpital, mon ami, right? Because you say, all right, well, what can we do? Well, if we apply l'hôpital, it says you take the dirt of the top, divided by the dirt of the bottom. Now, I should say not every 0 over 0 is l'hôpital, but most times when it's 0 over 0 and you don't see any simple algebra, l'hôpital is a good choice. All right, derivative of cosine, well, that's negative sine. Now, but remember, chain rule, multiply the derivative of the inside, that'll give us 3. So minus 3 sine of 3t, derivative of minus 1, 0. And then derivative of minus t squared, minus 2t. Downstairs, derivative of e to the t is e to the t. Derivative of e to the minus t, well, it's minus e to the minus t. And that minus is coming from the chain rule. Derivative of minus 2, 0. Good. Right. We're done, right? Well, let's check. And remember, whenever you're doing a problem, you can always say, all right, I did a step. Now let me come at it with fresh eyes. In other words, I'm not going to worry about that anymore. I'm going to be focusing on that. So what do? I do the same thing that I did before, right? Plug in 0. So what happens? Well, upstairs, sine of 0 is 0. Then you get minus 2 times 0, which is 0. Downstairs, e to 0, 1, minus e to the minus 0, minus 1, which is 0 over 0. And what does that equal? That's right. More work. Okay, good. Okay, so what's our more work? Well, we go back to l'hôpital. Ah, l'hôpital, mon ami. Oh, let us get the baguette. Let us eat the croissant. You know, we're going to work with our l'hôpital. So, and when you're taking l'hôpital, remember, it's not a quotient rule. Take the derivative of the top, take the derivative of the bottom. Okay, derivative of the top, well, derivative of sine, cosine. And then there's going to be a 3 come out, so minus 9 cosine 3t. Well, the derivative of minus 2t is minus 2. Derivative of e to the t, still e to the t. And the derivative of e to the minus t is minus e to the minus t. There's already minus there. So 2 minuses make a plus. All right. Now, what does that go to? Well, notice downstairs we're going to get e to the 0 plus e to the 0, which is not 0, which means we're done. So what do we get upstairs? Well, we're going to get minus 9 minus 2, which is also known as minus 11. And downstairs, e to the 0 plus e to the 0, which is 2. So, minus 11 over 2. And that's it. And we're done. That was fun. Okay, good. A nice warm-up. All right. Well, you know, you could do l'hôpital many times. It just depends on the problem. And so you do it as often as you need. All right. Ooh, this one looks interesting. Find the limit as x goes to 0. Secant of x to the power 1 over x squared. Now, what is this doing? Again, plug in 0. Well, what's happening? Secant of 0. Well, secant of 0 is 1. It's Just think of it as like 1 over cosine of 0. 1 over cosine of 0, 1 over 1. Now, 1 over x squared. Well, if x is going to 0, x squared is going to 0 as well. So it's a very small, tiny number. 1 over a very tiny number is a huge number. So this is getting arbitrarily big, meaning infinity. Now, what is 1 to the infinity? Well, you might think it's 1, but no, it's not. The answer is, it's more work. Now, you might be wondering, why do we call it more work? Well, because it's easier than trying to spell indeterminate, which is a hard word to spell. More work is easy to spell. All right, so it's indeterminate, meaning we have to do more work. So you're like saying, okay, let's do le hôpital, right? Right? Wrong, not yet. What's our problem? Well, notice the form. It's something to a something. Now, if I want le hôpital, I have to have something divided by something. I have to have a fraction. I don't have that. And if I think about it, well, I really have a function raised to a function. So what I want to do is I somehow want to bring this down. That would be ideal. If I could bring this down, then I could get a fraction. Well, how can you bring exponents down? Well, the easiest way to bring exponents down is using the power of log. Logs are a very useful tool. So for a second, let's call our answer, we'll call L for limit. L is limit as x goes to 0 of secant of x to the 1 over x squared. Now, we want to bring it down, so we're going to use log. So, log of L is going to be, and the nice thing about log is you can push it into the limit. That's the limit as x goes to 0 of log of secant of x to the 1 over x squared. Well, that's the same as, now we're using the power of the log. See, the 1 over x squared comes down. So, that's log secant of x, and that 1 over x squared, it's like I can write it as x squared in the denominator. Good. All right, so there we go. Now, what does this do? Well, this goes to log of 1 over 0 squared, which is 0 over 0, which is more work. Not surprising, but notice it's the good kind of more work. It's the more work which is fraction over fraction. So, what do we do? Aha! Oh, yes, exactly. It is time for us to do the le hôpital. Have the fish, which he would call the poisson. All right, so we're going to do le hôpital. So that's the limit. X goes to 0. And notice, by the way, when we do le hôpital, we indicate we're doing le hôpital, and we always check. So if you're going to do le hôpital, you always have to check that you can apply it. Because if you don't check, well, it may not apply. But more importantly, if you don't check, you could lose points. And our goal is to get all the points. Okay, so what do we get? Well, the derivative log of secant of x. So how do you take the derivative of log? Well, it's 1 over the inside, but then you multiply it by the derivative of the inside. Derivative of secant is secant times tangent. Derivative of x squared, 2x. Now, we can simplify. You should always clean it up. The secants cancel, so really we have the limit as x goes to 0 of tangent of x divided by 2x. And what does that go to? Well, tangent of 0, 0. 2 times 0, 0, which is more work. My gosh, we get to do a lot of work on this problem. But notice, we keep getting simpler and simpler. Tangent of x over 2x, that's a whole lot more simpler than where we started at. All right, so what do? Well, we once again visit our good friend, le hôpital. Le hôpital. How are you? All right, let us see. Oh, all right, derivative of tangent, secant squared x. Derivative of 2x, 2. And now what do we see? It's game over. Game over, man. How do we know? Do you see that 2? Well, that 2 doesn't become 0. It's always 2. So we're not going to get a 0 over 0. So there's no more work ahead of us. We just have to figure out what is it. Well, what is secant squared of 0? The answer is 1. And what is 2? It's 2. So, aha, we got it. A half. That's our answer. Right? Right? Be careful. Okay, let's follow this. What does a half actually equal? So we start going backwards. We start going backwards. We go backwards. And we say, oh, it's not our answer. We have that the log of our answer is equal to a half. So how do we get our answer? Well, we got to get it outside of the log. And how do we get rid of logs? We get exponentials. So L, our answer, that's e to the log of our answer, which is e to the 1/2. And by the way, e to the 1/2 is also known as the square root of e. Now, that's probably something you wouldn't have guessed, right? If you see secant of x to the 1 over x squared, you're not thinking, hey, square root of e. Exactly, right? No. You wouldn't guess it. But you see, we don't have to guess. We can work out the answer. That's even better than guessing, because then we know for sure. All right. Next one, number 3. So given that f of x is twice differentiable, all right, that means that we can take 2 derivatives. And the limit as x goes to 2 of x, f of x plus 4 over x minus 2 squared equals 3. Find f of 2, f prime of 2, and f double prime of 2. Now, in some sense, this is kind of interesting. See, we are told, here's what the limit is. So we know what the limit is. Now all we have to do is figure out, okay, given what we know what the limit is, what can we say about various pieces of our function? So oftentimes we have the function, and we're trying to find the limit. We're turning it around, going the other direction. All right, well, let's figure this out. So let's think about the problem. So we have the limit as x goes to 2 of x, f of x plus 4, divide that by x minus 2 squared. Now, we do what we always do whenever we have a limit, which is let's plug in where we're going to. In this case, we're going to 2. So this goes to 2 times f of 2 plus 4. Downstairs, 2 minus 2 squared, that's 0. All right, now at this point you're probably thinking, all right, well, what does that mean? Well, notice something. Does this limit exist? The answer is yes. And how do we know that? We know the limit exists because it says it right here. We know the limit is 3. So the limit has to exist. Now notice we have something over 0. Now, when can I have something over 0 exist? Well, if the numerator is anything other than 0, it's not going to be a finite number. Because if it's a non-zero number divided by 0, what it means is that your function, it's blowing up. It has some kind of asymptote. Or maybe it's going to negative infinity. But it can't exist. So that says, hey, we need this part, the top, has to equal 0 for a limit to exist. Well, what does that tell us? Well, it tells us that 2 f of 2 plus 4 has to equal 0. So 2f of 2 equals negative 4, or f of 2 equals negative 2. So that's what we know. All right, good. So we now know what f of 2 is. That's part of our answer. And now we can say, aha, so this is now 0 over 0. Well, 0 over 0, what do? Well, you do more work. More work. And of course, our more work is le hôpital. Oh, le hôpital. Oh. All right. So what do? So we apply le hôpital. So limit as x goes to 2, derivative of the top, x, f of x. What rule do you need to take the derivative of x times f of x? Well, we need the product rule. So derivative of the first, that's 1 times f of x plus x times the derivative of f of x. Well, we don't know what f of x is, so we just write f prime of x. And the derivative of 4, 0. Good. Downstairs, derivative of x minus 2 squared. Well, think chain rule. 2 comes down, so it's 2 times x minus 2 to the 1 times the derivative of x minus 2, which is 1. All right. So, again, we have a limit. Let's plug in 2. What do we get? Well, this goes to f of 2 plus 2 f prime of 2. Divide that by 2 times 0. Now, we know a couple of things. We know what f of 2 is, so that's negative 2 plus 2 f prime of 2, and 2 times 0 is 0. Now, same idea as before. Look, we have something over 0. In order for the limit to exist, what needs to be true? Well, the same idea. We need that the top has to equal 0 for our limit to exist. Well, what does that tell us? Well, it tells us that minus 2 plus 2 f prime of 2 has to equal 0. And so, okay, move that minus 2 across. 2 f prime of 2 equals 2. So f prime of 2 is 1. All right, there's another part of our answer. Okay, but what do we have? Well, now we have that this is 0 over 0. So we do more work. But that's okay. We're almost there. L'hôpital. One more time, my friend. All right, limit x goes to 2. All right, upstairs we have the derivative, f prime of x, then product rule again, plus derivative of the first is 1 times f prime of x, plus x times the derivative of f prime, which is f double prime. That's going to be divided by derivative of 2 times x minus 2 is 2. And now we're like, whoa, game over, right? Because that's not going to be 0. So what's that limit turn out to be? Well, there's 2 downstairs. We're going to get f prime of 2 plus f prime of 2. So that's 2 f prime of 2. But remember, f prime of 2 is 1. So that's going to be 2, right? So f prime of 2 plus f prime of 2, 1 plus 1, plus 2 f double prime of 2. Okay, now at this point you're like, well, wait, the top doesn't need to equal 0. How do we figure out what the top needs to equal? But remember, we know what the limit is. The limit is 3. So this has to equal 3. All right, multiply by 2, we get that 2 plus 2f double prime of 2 has to equal 6. Subtract 2, 2f double prime of 2 has to equal 4, and divide. F double prime of 2 has to equal 2. And now we have our pieces. So we're ready to say what our answer is. So our answer is f of 2 is negative 2. F prime of 2 is 1. That's from here. And f double prime of 2 is positive 2. That's it. That's the answer. Cool. Yeah, this is fun. That's a fun puzzle. All right. Well, I think that might be our last L'Hôpital problem. All right, L'Hôpital. Thank you, my friend. Thank you. All right, number 4. So, for y equals 1 over 1 plus x squared, find the value a, positive, where the y-intercept of the tangent line at x equals a is maximal. So let's sort of get an idea of what's happening here. So 1 over 1 plus x squared, if you were to sketch it, it looks something like this. Something like that. That's a bit sketchy, but that's okay. It doesn't have to be perfect. And now what's happening? Well, what we're saying is, you come to a particular value. Let's say here's our value, here's our a, and then at that a, you say, all right, where's that tangent line? And now, whatever that tangent line is, it's going to hit the y-axis somewhere. Now, the question is, how should we pick a so that this intercept is as high up as possible. We want it to be big. We can see this as a really bad choice. And you might say, how do we know it's a really bad choice? If I take the tangent line there, I'm going to be hitting it higher. So yeah, there's good choices and there's gooder choices. Well, we usually say better choices, right? So what's the best? What's the best? Well, all right. So we need to figure out what we're optimizing. So that means we need to make a function. This is an optimization problem. Now we know it's an optimization problem because we see this word maximal. So it means we're trying to make it as big as possible. That's optimization. So we need a function. Now, is this the function we're trying to optimize? Well, no, it's not. What are we trying to optimize? Well, the y-intercept of the tangent line. That's what we're trying to optimize. So we need to write the y-intercept of the tangent line as a function. So let's start thinking about it. Well, first off, let's just start with something we're comfortable with, namely the tangent line. We can do that. So we learned that, right? So it says if you have a function y equals f of x, and the tangent line at x equals a is done by the following. Namely, you're going to have y minus f of a is equal to f prime of a times x minus a. So the a comma f of a is the point, f prime of a is the slope. So this is the slope point form. Now, let's rewrite this. We'll move the f of a across, so you get y equals, and we'll distribute the f prime of a through, f prime of a times x minus a f prime of a plus f of a. Now, this is our slope, and this part right here, this whole expression, that's our intercept. Okay, so that's what we're after. So let's suppose we know our function right now. Our function here is 1 over 1 plus x squared. So we'll make this little side note here. So f of x is 1 over 1 plus x squared, or we write that as 1 plus x squared to the minus 1. What's f prime of x? Well, minus 1 comes down, 1 plus x squared to the minus 2, and then we're going to multiply that by the root of the inside, which is 2x. Or you could write that as minus 2x over 1 plus x squared squared. So here we go. So I'm going to use this formula here. So our intercept, our y-intercept is, excuse me, we're going to think of this as some function. I'll call it capital F at a. So we're making a function. So that is minus a times, plug a into the derivative. So minus 2a over 1 plus a squared squared plus the function at a. So our function, that's 1 over 1 plus a squared. Now, minus minus makes plus. So that's 2a squared divided by 1 plus a squared squared. Now, if I wanted to add these together, I'd get a common denominator. So plus 1 plus a squared over 1 plus a squared squared, because I multiply top and bottom by 1 plus a squared, which makes this 1 plus 3a squared. Divide that by 1 plus a squared squared. Good. Now, that is what we're trying to optimize. Now, we're ready to start. Seems weird to say that because it feels like we already did a lot of work. But we know where we're after, right? So this is what we're trying to optimize. So what do? Well, time for us to take our derivative. So when we're doing optimization problems, we find our function and then we take our derivative and look for critical points. So here, we'll use the quotient rule. So what does the quotient rule say? It says, let's take the bottom, 1 plus a squared squared times the dirt of the top, which is 6a, minus the top, 1 plus 3a squared, times the dirt of the bottom. Well, chain rule, 2, 1 plus a squared to the 1, times the derivative of a squared, which is 2a. All that divided by 1 plus a squared squared squared, because you square the bottom. Now let's try to simplify. What can we do? Well, here are some things that we can do. We can say, let's factor out what's common. So looking in the numerator, what do they have in common? Well, they have 1 plus a squared, because here it's to the 1 power, here's to the 2 power, so we'll factor out 1 plus a squared. We can also factor out a 2a, because I see a 2a. 6a, well, 2a divides into that. And now, if I factor that out, what's left? From the first term, I need a 1 plus a squared. And the 6a, well, I pulled out 2a, so I'm left with 3. Minus, now here, I got sort of the end part, but I didn't get this part. So I'm going to distribute that 2 through, and also I'm going to distribute that minus through. So that would be minus 2, and then minus 6a squared. And downstairs, 1 plus a squared to the 4th. Now, of course, we can cancel off a single 1 plus a squared. That's nice. And we should factor this through. So, what do we have? Well, we have 2a. Then we have 3 minus 2. Well, if I take 3 minus 2, that's 1. Then we have 3a squared minus 6a squared. So that's minus 3a squared. And divide that by 1 plus a squared cubed. Now, critical points. Well, where are our critical points? The denominator is always positive. There, no critical points there. All right, how about the numerator? Well, when does the numerator equal 0? Well, 2a equals 0 at a equals 0. All right, how about 1 minus 3a squared? Well, that would be 1 minus 3a squared equals 0. If I move the 3a squared across, 1 equals 3a squared. If I divide by 3, I get a squared equals 1/3. And then I take the cube root, plus or minus. So we get plus square root of 1/3 minus square root of 1/3. Now, what are we after? We're after the value of a, which is positive, which maximizes it. Now, we're told a has to be positive, right? So it can't be the 0, can't be the negative, which means we only have one candidate left, and that's our answer. So it must be the square root of 1/3. Now, technically, what should we do? Well, technically, if we wanted to be really, really careful, we would test square root of 1/3. In other words, what we would do is we would say, okay, well, let's pick something on either side. And we'll skip that step. But I can tell you, if you pick something between 0 and square root of 1/3, pick something small like 0.001, right? It's still positive here, and it's 1 minus a small number, which is positive, which means below square root of 1/3 we're increasing. If you pick something big like 1,000,000, positive and very negative, which means we're going decreasing after square root of 1/3. So the square root of 1/3 is indeed a max, and therefore that's our answer. A equals the square root of 1/3. Now, you might think to yourself, wait a second, that seems oddly familiar. Isn't it the case that the square root of 1/3 is not just any random point for this function? It seems like it's something special. All right, do you see what it is? Well, maybe not so clear. It turns out this is an inflection point. Now, let's see if we can figure out why that would be true. Well, remember, we have our generic formula here, and we actually substituted in. Well, let's suppose we ignore that and we're to take the derivative here. What would that derivative be? Well, we have a little bit of space. We'll see if we can squeeze that in. So product rule, so it would be minus, derivative of the first is 1, f prime of a, and then minus a times the derivative of the second, f double prime of a, plus the derivative there, that's f prime of a. And notice those terms cancel. So when we're looking for the critical points here, well, it turns out we're looking for when does minus a times f double prime of a equals 0. So that tells us we get a equals 0 and inflection points happening. So it turns out, kind of interesting fact, that when you're looking for maximal intercepts or minimal intercepts, they will happen at 0 or inflection points or at boundaries, should we have them. Interesting little side note. All right, cool. Okay, but now on to the next one. Number 4. Oh wait, no, that was number 4. Number 5. What is the area of the largest rectangle you can make where the bottom edge is on the x-axis and the top two corners lie on the curve y equals e to the minus x squared? Now, if you think about the curve y equals e to the minus x squared, it's kind of similar to the last one. It has this shape. In fact, you might describe it as kind of a bell shape. Now, why do I say that in that very mysterious voice? Well, it turns out this is a very special curve, and this is called the bell curve. And it's an important curve if you're doing statistics, for example. Now, so what do we have? Well, what we have is we have this rectangle. And it looks something like this, because the bottom edge is on the x-axis, and we have our shape, and our goal is, what are we trying to make? Well, notice it's the largest, so we know our optimization, and largest area. All right, so what do we need to do? Well, we need to figure out the dimensions of this rectangle. So let's suppose this is at x. Well, how large is the base? And again, bad picture. This is, my axis is a little bit crooked. It's probably more like that, right? So there's symmetry. E to the negative x squared is a function which has symmetry. It's an even function. So if this is x, the base would be 2x. What's the height? Well, the height is going to be up to the function, e to the minus x squared. So now I know the base, I know the height, so the area is base times height. All right, cool. So what do? Well, now that we have our area, it's a function of x, and so we can really call this our a of x. So what we'll do is we'll take the derivative, a prime. So product rule, derivative of the first, 2 times the second, e to the minus x squared, plus the first times the derivative of the second, chain rule, e to the minus x squared times the derivative of the exponent, minus 2x. So let's see. We can definitely pull a 2 out, and we can also pull out e to the minus x squared. And if we do that, what do we have? Well, from the first term we have a 1, and then what do we have from the second term? Well, I pulled out the e to the minus x squared, I pulled out a 2, so I'm left with an x and a minus 2x, so that's minus 2x squared. Now, well, we're looking for critical points. Can e to the minus x squared, can that ever be 0? No, never. Could never be 0. All right, so that means we got to look here. So 1 equals 2x squared. All right, so a half equals x squared, or x equals plus or minus 1 over root 2. Now, notice there's sort of an implicit thing here. We're really assuming x is positive, because it's symmetry, right? If you do x is negative, well, that wouldn't make any sense, right? Because your area would be a negative area. But we say, look, as long as x is positive, because of symmetry, we're good to go. So our max happens at, at x equals 1 over root 2. Now, is this our answer? No. No. Why not? You see, we're not after where, we're after what is the area. Our answer should be an area. That's what our answer needs to be. So we need to figure out what the area is, not for which value of x that happens. See, they could have asked several questions like, what's the value of the x? Or what are the dimensions? So, what's the base? What's the height? They asked us for the area. So what do? Well, we plug stuff in. So our area at 1 over root 2, that's our maximal area. That's equal to 2 times 1 over root 2 times e to the minus 1 over root 2 squared. Now, we can clean this up a little bit. 2 divided by root 2 turns out to be square root of 2. And this is e to the minus a half. And we can actually play around with this. This is the same as square root of 2 divided by e to the 1/2, because that negative means put it downstairs. And e to the 1/2 is like square root of e. So this is the square root of 2 over e. And that's our answer. Well, of course, most of that is just saying, well, let's rewrite it in an interesting way. All right, so that's the area of the largest rectangle. Good. And of course, I should have pointed out the top 2 corners. Yeah. I should have said that when I said that here. Okay. Now, number 6. Okay. For a greater than or equal to 0, find the point on the curve y equals root x closest to the point a comma 0. So we have the following. We have the curve y equals square root of x. So that does something kind of square root like. So there's our curve y equals square root of x. And then we have, all right, here's our point A. And we're trying to find what's this point, the point which is closest to A. Now, how can we do it? Well, we got to find a formula that we need to optimize. So let's think about what's the right formula here. So first off, we have an optimization, because you see how we have the word est. Est is shorthand for optimization is the best thing to do here. No. Whenever you have est, that means you're optimizing. Now what are we optimizing? Well, close est. Now when we're talking about closest, that really means distance. So this is an optimization problem that involves distance. We want to get our distance as small as we possibly can. So we need to figure out what's our distance from A to that curve. Well, I don't know the smallest distance, but what I could say is that a point on the curve looks like the following. X comma square root of x. That's what a point looks like. So the distance formula, which I'll say it's a function of x, it's equal to the square root of, now this point, by the way, I wrote it as a, it's really a comma 0. So it's x minus a squared, you take the difference here in the x coordinates, plus square root of x minus 0 squared. All right, now we can clean this up. Notice that there's a square root here. It would be nice if that square root weren't there. So how do we get rid of it? And the answer is we just get rid of it. Well, so we'll make up this new function. I'll call it little d of x, which is x minus a squared plus, and of course, square root of x squared would be x. Now you're probably thinking, Wait, that's cheating. You can't just get rid of a square root. Can you? That'd be nice, right? Well, let's think about it. So why can we get rid of a square root? Why haven't we actually cheated? Well, the reason we can get rid of a square root is if I'm trying to optimize the square root of an expression, in other words, make it as small as possible or as large as possible, I just have to optimize what's on the inside. Because it turns out the square root, it's a very special type of function. And namely, we actually have a name for it. So the square root is what's called an increasing function. And you can even add the word monotonic. You remember that's the one drink kind of deal? Mono, one, tonic is a type of drink. No. Monotonic just means it's always increasing. So whenever you have something which is monotonic, well, if you want to optimize you just have to say, I just have to optimize the input. So we need to optimize the input. Now, here's something we have to be really, really careful about. And it's super, super subtle. So I'm going to pause for a second here and ask the question, is there anything else I should say about my function d of x? Namely this x minus a squared plus x. All right, do you see it? There's a restriction on x. Namely, x has to be greater than or equal to 0. So this says we're doing an optimization, but this is an optimization problem with boundary. So we have to be careful. So whenever you have an optimization with the problem with the boundary, you have to ask yourself the question, could the boundary come into play? Well, we'll get to that in a second. All right, so let's proceed as we would. So we take our derivative. So we're trying to optimize the input, right? So d prime of x. So the derivative would be, the 2 comes down, x minus a plus 1. And we say, all right, we'll set that equal to 0. And we say, okay, so that says x minus a times 2 equals negative 1. X minus a equals negative a half. Or x equals a minus a half. All right, so now where are the critical points? So the critical points are where the derivative equals 0. Now the derivative is never undefined. And is there any other critical point? The boundary, 0. All right, so now we have to make a decision. Well, what happens? Well, now you have to be really careful here because there's two things that could happen. So suppose a is bigger than a half. Well, that means that a minus a half is positive, right? Now, suppose for a second we were to take the second derivative. I know we don't often do this, but the second derivative. What's the second derivative? Well, second derivative here would be 2. And if you remember the second derivative test, where the second derivative is positive, your curve looks like that, which means that your second derivative at a minus a half would be a min. Okay, so when a is greater than a half, we get that x equals a minus 1/2 is a min. And so that has to be the minimum. All right, what happens when a is less than or equal to 1/2? Well, the problem is when a is less than or equal to 1/2, that point is gone because it's no longer in contention. Because what happens is a minus 1/2 is then negative. Well, you can't even consider it. That's outside our range of possibility, which means we only have one point. So that says that our closest point is x equals 0. That's the min. So this has two answers depending upon what a is. So if a is less than or equal to 1/2, so that means that you're like down here. Then that says the closest point is at 0, 0. So 0, 0, because we're after the point. If a is above 1/2, then the closest point, well, is at the x-coordinate is a minus half, comma, square root a minus a half. And that's our answer. So be careful. Be the right amount of careful. Now, the second case is like the case at what I'm over here. This has an interesting application. And because if you think about it, if you were to turn the square root curve sideways, what do you see here? Well, what you see is one side of a parabola. So, one of the things that you can get from this is that if you start with a parabola, so let's imagine we turned it sideways, and here's our parabola. It says, if you have a circle, which is a small circle, and in particular, if the radius is, so if the radius here is less than or equal to a half, it comes down and it hits the bottom. So it goes to the bottom. Because the closest point is at the origin. So it just settles down. On the other hand, if you have a very big circle, so you have a very large circle, so let's pretend that's a circle. So if the radius is bigger than a half, it doesn't hit the bottom. Why? Well, because it turns out that you're going to touch somewhere on the sides. That's actually what the conclusion is. It turns out it's a very similar problem. So if you wanted to ask the question, what's the biggest circle that you could actually have and have it touch on the bottom of this parabola? The answer is a half. That half is sort of like an interesting sort of transition between two behaviors. That, of course, is a slightly different problem. And it's sort of fun to think about. But anyways, that's our answer. All right. Number 7. Analysis of your past parties has led to the development of a chip index, n squared p, where n is the number of nacho chips bags that you have, and p is the number of potato chip bags that you have. Given that you have $18 for your chip fund, and a bag of nacho chips costs $3, and a bag of potato chips costs $1, how many bags of each chip should you buy to maximize the chip index and thus have a most awesome party? Okay, so what are we trying to optimize? Well, we actually know that. It's pretty simple, right? We're good to go. It's n squared p. Now you might say, well, perfect. Nothing needs to happen. Except, notice this has two variables, n and p. Now that's outside of what we can do right now. We don't know how to optimize things with two variables. Not yet. That's going to be multivariable calculus. So we know single variable. We need to get down to one variable. One variable to rule them all. So how do we do it? Well, we think to ourselves, say, all right, there must be more information. So let's see, there's some numbers they throw us. We have $18, and nacho chips cost $3, and potato chips cost $1. So if we spend our money, we have $18, so we get 3 times how many nacho chips we have, plus how many potato chips we have, right? Because it's 1 times the number of p, and 3 times the number n. So what this is, this actually gives us a relationship. So we can use this to solve for one of our variables. In fact, I think p is pretty easy to solve for. P equals 18 minus 3 times n. Now, that can be used to come back to our original optimization problem. We say, look, let's get rid of one of our variables. So I can write this as well, let me start with the n squared first, times 18 minus 3n. There we go. Right? N squared times 18 minus 3n. Or, that's 18n squared minus 3n cubed. Now, function of one variable, n. So, we're ready to do our optimization. So we take our derivative, 36n minus 9n squared. So there's our derivative. And let's factor out. We can factor out 9. We can factor out n. And then we're going to be left with 4 minus n. Okay, now, where are the critical points? Well, we could have n equals 0 or n equals 4. Now, at this point we ask, okay, which one is right? Well, notice if we don't have any nacho chips, what's our chip index? 0. It's not a party without nacho chips. All right, so yeah, that's a terrible choice. How about n equals 4? Well, we'll have something, right? So if n equals 4, what's p? Well, let's come over here. That would be 18 minus 3 times 4. 18 minus 12 is 6. Okay, so we're going to have 4 squared times 6. That sounds pretty good. That's a pretty high number. That's 16 times 6, 96. That's a really good index, right? So we should get 4 nacho chips, and we should get 6 potato chips. That's how we can maximize our index and have a most awesome party. Of course, I guess nowadays it's a party of 1, but that's okay. That's all right. Good. There you go. Number 8. We have another change here because we see different words. Newton's method. All right. Well, this shouldn't be so bad. I mean, we're starting calculus. Everything is Newton's method, right? He's the one who came up with it. So what do we have? So there's this function, f of x equals x cubed plus 2x plus 2, and x0 equals 2. Find the exact value for x4. Now, you might think, what's going on? Okay, so let's talk about what's going on. So when we're doing Newton's method, it's sort of the following. I'm after the problem of saying, this is what I want. That's my goal. And I want to find where that is. Well, that's hard. So we might say, okay, we have a guess. Here's our guess. Now, it turns out we're wrong. Well, that happens a lot. But we'll say, look, let's make a better guess. And what we'll do is we'll pretend like, hey, if this were a straight line, I would just follow the straight line, and then I'd get my answer. Well, I can use my tangent line to act like an approximation. That is a straight line. And now, that's our better guess. You'll notice it is better, right? Because I get closer. Now, of course, things can go bad. They sometimes do. But this is sort of a reasonable thing. Now, that's not perfect. So you might say, well, just repeat. So you keep repeating over and over. And if you repeat often enough, you'll oftentimes reach your goal. Now, things can go bad, but that's not what we're here to talk about. Now, what do these subscripts mean? Well, these are our guesses. So when you see a subscript 0, you oftentimes think of it as our very first initial guess. And this subscript 4 says that's going to be our 4th guess. Now, how do you get from one guess to the next guess? It's a nice formula which says our next guess, so our n plus 1th guess, that's equal to our current guess, which is, we call that our nth guess, minus the function at our current guess, divide that by the derivative of our current guess. Okay, this, by the way, this is about 60% of the work is to remember that formula. So let's do it for our case. So xn plus 1, to make our next guess, we take our current guess, subtract our function here, which would be xn cubed plus 2xn plus 2, divide that by, now what is f prime of x? Oh, we probably should have written that down. Well, we have time to do it now. F prime of x, that would be 3x squared plus 2. So 3xn squared plus 2. Now we could actually clean this up a little bit, right? We could get common denominator. So that would be 3xn cubed plus 2xn. That's this piece minus xn cubed plus 2xn plus 2. Now, how did I get that, by the way? I just multiplied by 3xn squared plus 2. Divide that by 3xn squared plus 2. The 2xn's actually cancel. So we get 3xn cubed minus xn cubed. So that's 2xn cubed. And then minus 2 over 3xn squared plus 2. Do you need to do this? No. But it's a way that if you're going to do several iterations, and we have to do 4 iterations, it can make it go a little bit faster. So, here we go. Now, this is a good time to be patient. And because we don't have a calculator, it's got to be the case that we just have to be really, really patient. So, and if our numbers get really weird early, probably we should be careful and double check. So x0 equals 2. x1, so I'm going to plug 2 into here. So that's going to be 2 times 8, because that's 2 cubed, minus 2. Divide that by 3 times 4 plus 2. So let's see, that's 2 times 8, 16, minus 2 is 14. And then here we get 12 plus 2, which is 14, which is 1. You notice that we really want to simplify. You should definitely simplify if you're ever going to use something again. Now here we're going to use the answer to x1 to get x2, so it pays to simplify. So all right, what about x2? All right, so now take the answer for x1. So that's going to be 2 times 1 cubed, which is 1, minus 2. Divide that by 3 plus 2. Well, the numerator is 0. Hard to recover from that. 0. All right, how about x3? What's that? Now we're going to put 0 in. 2 times 0, well, 0. Minus 2. Downstairs, 3 times 0, 0 plus 2. So, 2. So, minus 2 over 2, minus 1. Oh, wow, that's incredible numbers. All right, how about x4? By the way, this almost never happens. This just turned out to be a really happy coincidence. x4, well, 2 times minus 1 cubed, so that's 2 times minus 1, minus 2. Downstairs, 3 times minus 1 squared, that's 3 times 1, plus 2. So minus 2, that's minus 4. 3 plus 2 is 5. Minus 4/5. And that's our answer for the exact value for x4. If we wanted to, we could even write this in decimal, negative 0.8. Now what's the real answer? I don't know. In fact, that's what Newton's method, it doesn't find the real answer. It's all about finding a better answer. And if you do it often enough, you get something that's so good, you say, look, for all intents and purposes, that would be the right answer. All right. Number 9. Use Newton's method, starting with x0 equals 2, to get an estimate for a solution of x cubed equals 5 plus 5x, and give the value for x2. Now, at this point, you're probably thinking, wait a second, hold on. You just said that Newton's method, that's when we're looking for something of the form f of x equals 0. What do I mean by f of x equals 0? See, if you look here, come back here, our goal was, where do I cross? So where does the function equal 0? There is no function equal 0. It's like, I want one function, this x cubed, to equal another function. But here's the thing. We can actually rewrite that and say, look, move this across. That's the same thing as, I want x cubed minus 5x minus 5 equals 0. So I can think of this function, that's my f of x. So that's what I'm going to use Newton's method on. All right, so take the derivative, f prime, 3x squared minus 5. Now, our general formula says xn plus 1 equals xn minus our function at xn divided by f prime of xn. And we can just stay with this. We don't have to actually simplify if we don't want to. So x0 equals 2. x1, well, all right, that says plug in your previous guess, 2 minus the function at 2 divided by f prime at 2. So that would be 2 minus, all right, so now we plug 2 into our function. 8 minus 10 minus 5. 8 minus 10 minus 5. Downstairs, plug 2 into our derivative. That would be 3 times 2 squared, that's 12 minus 5. So what is that? That's 2 minus 8 minus 10 minus 5. Well, that's 8 minus 15. That's 7. Negative 7, right? 8 minus 15? Yeah, that's right. And downstairs, 12 minus 5, that's 7. Minus minus makes plus, so we really get 2 plus 7/7, which is 3. Okay, so that's x1. What's x2? Well, our previous guess, 3, minus our function at 3, divided by f prime of 3. So 3 minus, okay, plug 3 into our function. Well, 27 minus 15 minus 5. Plug 3 into our derivative. 3 times 3 squared, that's still 27 minus 5. So what's that? 3 minus, so it's 27 minus 20, so that'll be 7. And 27 minus 5 is 22. Now I can get a common denominator. 66 over 22 minus 7 over 22, which equals 66 minus 7 would be 59 over 22. And they don't have any common factors. And now you're like, oh, that's terrible. I don't want to do this again. We don't have to. We just need x2. So there's our answer. 59, 20 seconds. Now, you might think, wow, this would be great for a computer. You're right. This kind of method works great for computers because they love that kind of thing. For humans, not so much. It's terrible, terrible. All right. Well, number 10. Okay. So we're told xn plus 1 equals 4xn over 5 plus 4 over xn to the 4th, and x0 equals 137. And then we're told that the xn approach a particular value as n gets large. Determine what the value is. Well, so that says that what's happening is our xn is getting close to some number. Let's call it L. And we want to find what L is. Now let's do this in two different ways. So the first thing to say is, okay, let's just imagine n is getting big. What's happening to our xn? That says xn is getting close to L. So on this right-hand side, every term that has an xn is about L. So we're getting that it's going to 4L over 5 plus 4 over L to the 4th. On the right-hand side, what is xn plus 1 doing? So xn, that means if you have this big long list and you go out very far, the nth term is close to L. What is the n plus first term? So the one right next to it. So this is close to L. The one right next to it, what is that close to? Well, it's also close to L. So whatever the value is has to satisfy that relationship. Now from here, you can say, all right, well, let's subtract, because these both have L's. So if we subtract, we'll get 1L, subtract 4/5 L, is 1/5 L. That's the same as 4 over L to the 4th. Now fractions, cross multiply. That becomes L to the 5th equals 20. Well, what number, when I raise it to the 5th power, gives me 20? The answer is, it's the 5th root of 20. And that's the answer. All right, well, that was pretty quick. Let's do this another way. Suppose we were like, well, we look at this problem and we're like, well, what are we thinking of? And we have a little thought bubble and we're like, maybe this is newtons. Now, why do we think newtons? Well, the reason we might think Newton's method is because that's when it's saying like, well, here's something xn, and here's our next one, xn plus 1. Now, Newton's method says, I want xn plus 1 to look like xn minus my function at xn divided by the derivative of xn. So, let's be careful here. Let's try to gently massage this expression. So I have 4xn over 5 plus 4 over xn to the 4th. So first off, I'm going to have an xn in front. So suppose I have an xn in the front. If I do, what's left? Well, see how I have 4/5 xn? To get a 4/5 xn, that means I have to have minus 1/5 xn. So minus xn over 5 plus 4 over xn to the 4th. Yes? All right, so here's the thing, is my goal right now is to make this look like that. So I started by saying, let me put an xn in front. So far, I've gotten this part done. All right, next, I want to get a minus. Okay, that's not so bad. I'm going to pull a minus out. So minus xn over 5 minus 4 over xn to the 4th. Good. Now I've gotten to the minus. Now what? Well, I want the second part to be a fraction, because that should be a fraction. So, that's not so bad. Common denominator. Well, what would the common denominator be? Well, multiply it together. 5xn to the 4th. Well, what do I have to multiply the first time by? Well, I have to multiply by xn to the 4th. That would give me xn to the 5th. The second term I have to multiply by 5, minus 20. And now I say, okay, well, let's check. The numerator would be my function. So that looks like x to the 5th minus 20. What's the derivative of x to the 5th minus 20? 5x to the 4th. So I'm like, perfect. All right, now I've made it look like that. So I say, aha, and you can see, I've said aha because I even wrote it down. So this is Newton's method for the function f of x equals x to the 5th minus 20. Now that I know that it's the Newton's method for x to the 5th minus 20, I ask myself the question, well, what is Newton's method looking for? So Newton's method says that this is looking for the root. So if Newton's method approaches something, it approaches the root. So that would be when x to the 5th minus 20 equals 0, or when does x to the 5th equals 20, or when does x equal the 5th root of 20. So that's what it's going to approach. You'll see that the answers are the same. They should be, right? Because there's only one answer. It's not like it's going to approach two different things depending on how we think about solving it. But that just shows you sort of like, okay, if you understand what the tool is, how can I take an expression and mold it to fit my tools? And this is a useful thing to do. In fact, one of the big common themes that you'll see in mathematics is, here, I solved the problem before. How do I take a different problem and make it fit the problem I'm working on? And if you can develop that tool, you'll have a tremendous amount of power given to you. All right, well, that's it for that quiz. Wow, only 2 more quizzes to go. Well, it's going to have lots of good stuff. So, all right, my friends, stay healthy, take care. See you next time. Bye.